And what we want to look at now is HVAC. So we're interested in heating, ventilation, and air conditioning. Mostly we'll be looking at the AC part, but this is a major area of mechanical engineering where the buildings, the air conditioning of the buildings, the heating of the buildings, large office buildings, as well as homes, of course. And so what we want to be able to do is condition the air for human comfort. And with that, I want to be able to regulate the temperature, the humidity, and the airflow. And there are other things, but we'll stick with these at the moment. So for comfort, I depend on what the temperature is. If it's cool and very humid, I don't like that as much because it feels sticky. And so I want to be able to regulate the amount of water vapor in the air as well. So the temperature matters, the humidity matters, and the airflow matters. I don't want air blowing at me because it feels uncomfortable. So I need to be looking at the velocity of the air that comes out. So I'm looking at all these aspects when we design HVAC systems. We're not really going to look at the airflow that much in this course. We're going to give an overview. If you're interested in this, then there are HVAC design courses, etc., that you would be taking. And so there are comfort charts. So there are comfort charts that indicate what the conditions are. So there are comfort charts. And Ashrae and so Ashrae is the American Society for Heating, Refrigeration, and Air Conditioning Engineers. And so what that is they look at this and they have volumes on practice in terms of how to do this. And we will borrow some charts from them, which they have available, and you can look up online. In this course, it's available on Blackboard as well. But what they've done in terms of a comfort chart is that they've done experiments with people, and they've looked at people say what was comfortable in different situations in terms of these factors and other factors. And I thought you'd find it interesting, just the outside airflow. So one of the things we have to consider when we're air conditioning buildings and spaces is how much fresh air you have and how much recirculated air you have. So the fresh air, you want new oxygen to come in. And so for a lecture classroom, we're looking at about 7.5 CFM, cubic feet per minute, per person. So that's the fresh, so when you design the system, they're going to tell you this is the standard for an office, and they assume 65 people per 1,000 square feet. So they're looking at, so anyway, we're packing them in a little tighter. In an office, in contrast, in an office, we'd need 5 cubic feet per person, but they're only looking at 5 people per 100 square foot. So they're looking at bigger offices, 200 square feet. They probably have to modify that now into smaller spaces. And so as the space gets smaller, the CFM goes up, or the space per person gets smaller. And another thing you might find interesting is we generate heat. So when we're sleeping, we generate heat. When we're sitting, when we run, whatever. So we generate heat. Again, this is determined by Ashrae. And for a person, it's about 300 BTUs per hour when you're sleeping. And it's about 400 BTUs per hour sitting. And so this is heat generation within the space. So not only does heat leak in from outside, or you have heat flow in or out, but you're also generating it based on the people. So if I'm in this classroom with 65 people, I can multiply 65 times 40, and that gives me the heat load right away of what those people are contributing to the space that I need to remove or certainly be aware of. And it depends on the size of the person and all that sort of stuff. But again, that isn't part of our purposes here. It's to show what this is. And now what we have in terms of being able to determine the air's energy quality, or I was going to say quality because the aspects of that. We have something called a psychometric chart. And this is in the appendix. It's on Blackboard for this course. So we have something called a psychometric chart. And there are many. Carrier provides them, Ashrae provides them. It's in the appendix. And so what you're going to do is I want to explain how to find properties on this chart. So obviously I can't project the chart here. I'll draw a schematic of it. So we have the psychometric chart. You're going to have a line like this that goes up on the line here. And down here are the temperature dry bulb. So this is your dry bulb temperature going along the bottom. This is your wet bulb temperature. So this is T wet bulb. Remember in chapter 11 we talked about wet bulb temperature. This is your line of enthalpy. So you'll see a line of enthalpy here. You'll see lines of relative humidity. So I'll see relative humidity like 60%, 80%. And you'll also see lines of specific volume. So I have so what we have here, and over here, I'm going to have omega. So there'll be lines over here for the absolute or specific humidity. So I'll have omega values here. So I can find omega, relative humidity, specific volume, enthalpy, dry bulb temperature, etc. So I can find all this stuff. And so I don't have to calculate it as I did in chapter 11, but I can look it up on a chart. And so with that, if you would get the chart from Blackboard or from the appendix or from online, and we're going to be looking at English units, I'll give you some examples. So let's say that we have 80 degrees Fahrenheit and V is equal to 50%. And I want to find various properties. So now let's go in and we'll look at how to do this. So the first thing I'd like you to do is look and see, here's this line of 50%, here's 80 degrees Fahrenheit, here's the enthalpy, and the enthalpy lines look like this. So now what you do, so I want to locate this point. So I go up at 80 until I hit 50%. So that's the point I'm interested in. Now, if I want to read the enthalpy, it's a line like this. And I just read the enthalpy value off the enthalpy chart. If I want to determine the dew point, so with this, and if I want to determine omega, I read it over here. So what you should find, if you do that, is that we have T dew point is about 60 degrees Fahrenheit. Now, one of the things you'll notice is that this is not precise in that there'll be some variation. You could say, I get 60.3. It's all fine. We get an enthalpy of 31.6. We get omega of 0.0112. And we get a specific volume of 13.85. You will particularly find that the specific volume terms vary greatly. So the specific volume terms vary greatly, but see if you can find those. And so that's how you use the chart. So this is how we use the chart. Now let's look at something where we're going to have some cooling going on, and I want to move from state 1 to state 3, and I want to change the specific humidity. So I want to change omega. So I want to get rid of some water vapor in the air. So this is, so if I look at this, I'm here at 1, and I want to get down to 3. So what I'm interested in is going from 1 to 3. The only way I can do that is that I have to bring it to the dew point, reduce omega, and then reheat it. So I'm going to go from 1 down to 2, and then I'm going to, so from 1 to 2 is cooling, 2 to 3 is reheating. Now let's put some numbers on this. So we have an example with numbers. And so let's say I have a duct, and we'll have some cooling going on. We'll have some heating going on. We're going to start with 2,000 CFM, cubic feet per minute, 85 degrees Fahrenheit, and 50% humidity, relative humidity. And this is state 1, state 2, and state 3, which is what I wanted it at 70 degrees Fahrenheit and 50% relative humidity. So now let's look up and find out what these various enthalpy, omega, and specific volume values are. So I found that H1 was equal to 34.7. Omega 1 was equal to 0.0128. Specific volume 1 was 14. H3 was 25.5 BTUs per pound mass. Omega 3 was 0.0077. H2 is 20.5, and obviously omega 2 equals omega 3. And the dew point was about 64 degrees Fahrenheit. So you can find these values. And now let's start the calculations, and we'll find the mass flow rate rather than volume flow rate. And so the mass flow rate at state 1, and the mass flow rate stays constant, is 2,000 cubic feet per minute divided by 14 is equal to 142.9 pounds mass per minute. The cooling, Q dot cool, is equal to the mass flow rate times H1 minus H2 is equal to 142.9 times 34.7 minus 20.5. So we have Q dot cool is equal to 2029 BTUs per minute. So that's the cooling rate. If I divide by 200 BTUs per minute per ton, we'll see that there's a little bit over 10 tons. 10.1 tons. I'll write the 10 better. And then we'll find the reheating. Q dot reheat is equal to m dot times H3 minus H2 is equal to 142.9 times H3, 25.5 minus H2, 20.5. And so we have Q dot reheat is equal to 714.5 BTUs per minute. And let's see how much liquid came out. So we cooled this, so we have the liquid come out, and m dot of the liquid is m dot A times omega 1 minus omega 2. $142.9 times 0.0128 minus 0.0077. And so what we have is the mass flow rate of the liquid is equal to 0.729 pounds mass per minute. So this is this liquid you see on air conditioners. It's the water that drips out, and so we see what that is. Now, so this was for cooling, so we wanted to cool and we reheated, we did that, and so we can see what this looks like on the psychometric chart. There's also issues when we come to heating, and that we have to be aware of, particularly in the wintertime, that we often need to heat and humidify, because when we heat up outside air and omega stays constant, the relative humidity decreases significantly, and our bodies don't care for that, very dry air. So if I were to look at, we're going to heat and humidify, but let's just first look quickly at why we have to do that. I take a psychometric chart, and if I'm starting here, and let's say this is 40 degrees Fahrenheit, and I'm at, P is equal to 80%. So I'm there, it's 40 degrees, it's a cold fall day, and now I'm just going to heat that air up 1 to 2, and I'm going to be here at 75 degrees Fahrenheit, and then I'll find that the relative humidity is 22%. So it's dry air, and what happens is with the mucous membranes in your nose, your mouth, etc., they get dry and it's not as comfortable. So what we want to be able to do is have the air at 75 degrees, but we'd like it to be a little more humid, which we find more comfortable. And that's why we introduce humidification. The chalk on my fingers makes it hard to turn pages, so that's part of what's going on here. So now let's set up a problem where we're going to have an example where we do humidify, and we'll go through putting some numbers in so you see how this works. So we're going to heat, and then we're going to humidify. We'll squirt some water in. And so we'll have H2O at 50 degrees Fahrenheit, and H is equal to H sub F is equal to 17.7 BTUs per pound mass. And at state 1, we'll have 1,000 CFM, 40 degrees Fahrenheit, 80%. In state, and then over here in state 3, 1, 2, 3, we're going to have 75 degrees Fahrenheit and 50%. So what we want is we start here, and we want this, and we have to humidify to get there. And so what happens is that in heating systems, there'll be sometimes a built-in humidifier that will have water vapor evaporate into the warmed air. So now if I look up the enthalpy values at these various states, so H1 is equal to 14, specific volume 1 is equal to 12.7, omega 1 is equal to 0.0044, H3 is 28.4, omega 3 is 0.0094. And so the first thing I want to do is find the mass flow rate. We'll do a first law analysis and all that sort of stuff. So the mass flow rate of the air is equal to 1,000 divided by the specific volume 12.7 is equal to 78.74 pounds mass per minute. So that's a 7. So 78.74 pounds mass per minute. And now what we want to do is do a first law analysis on this whole system and find out what's going on. So we want to see what heating is required. So if we do a first law analysis, we have m dot A H1 plus q dot 1 to 2 plus m dot F HF is equal to m dot A H3. So that's what's leaving. And m dot F is equal to m dot A times omega 3 minus omega 1. So m dot F is equal to 78.74 m dot A times 0.0094 minus 0.0044. So I do that, and I'll find that the mass flow rate of the liquid is 0.393 pounds mass per minute. So it's not very much compared to the other one. And now I can do the first law analysis. And so Q dot is equal to m dot A times H3 minus H1 plus m dot F HF. So we have 78.74 times 28.4 minus 14 plus m dot F 0.393 times 17.7. I do this. So now if we do this calculation, we get that Q dot is equal to 1133.8 plus 7. So the amount I have to worry about from this term is 7 out of over 1,000. So it's not significant. So Q dot is equal to 1140.8 BTUs per minute. And for homework for you, so you can do some of these problems, we have homework 16.31 star, 16.35 star, 16.37 star, 16.43 star.